Welcome. Let this be the hour where nothing is asked of you. Let your breath slow, your shoulders release, your eyelids grow heavy. There is nowhere to be tonight, nothing to solve. Tonight, we simply look up together and let the stars carry your mind toward rest. The sun is one star among more than 100 billion in the Milky Way. Each one burns quietly in the dark, scattered across a disk so wide that light itself needs 100,000 years to cross it. Our star is unremarkable in size, ordinary in color, one small ember among countless others. Yet from where we stand, it is the only sun we have ever known. The nearest star system to our own, Alpha Centauri, sits about 4.24 light-years away. That distance sounds small when spoken aloud, but light itself would need over 4 years to make the crossing. No spacecraft humanity has ever built could reach it within a single lifetime. It waits there quietly, a faint triple star glimmering in the southern sky. Light from the sun takes about 8 minutes to reach Earth. In that short span, warmth crosses 93 million miles of empty space to touch your skin. The sunlight filling a quiet afternoon left its source before you ever noticed it was gone. Even something so close still carries a small, gentle delay through the dark. Voyager 1 is the farthest human-made object from Earth. Launched in 1977, it now drifts far beyond the planets, carrying a golden record of Earth sounds into the silence. It moves alone, unhurried, sending faint signals back across the dark. No human hand will ever touch it again. Voyager 1 has traveled less than 1,000th of a light-year in over 45 years. It moves faster than any bullet, yet the galaxy makes it seem almost still. At its current pace, reaching the next star system would take tens of thousands of years. The vastness of space humbles even our fastest machines. The speed of light is the universal speed limit in physics. Nothing observed has ever exceeded it, and every equation we trust confirms its ceiling. It defines how quickly cause can lead to effect, how far a signal can travel before time runs out. This limit shapes the very structure of the universe. No object with mass can reach the speed of light. As anything approaches that threshold, it would require infinite energy to go faster still. Physics allows massless particles like photons to move at that speed, but matter itself is held gently back. It is a boundary written into the fabric of reality. Chemical rockets are the only propulsion technology ever used to launch humans into space. Every crewed mission, from the first orbits to the moon landings, relied on burning fuel and oxidizer together in a controlled release. It is a method both ancient in principle and still unmatched in reliability. For now, it remains our only proven way off the ground. The Saturn V rocket produced 7.5 million pounds of thrust. It remains the most powerful rocket ever successfully flown, lifting astronauts toward the moon on pillars of fire. Its size dwarfed anything before it, taller than most buildings of its era. And yet, even that immense power could barely leave our own solar neighborhood. Let your breath begin to slow now, just a little more with each cycle. Notice the inhale arriving without effort and the exhale growing longer, looser, like a tide pulling gently back from shore. There is no rhythm to force here, only the one your body already knows. Each breath out can carry a little more weight from your shoulders, your jaw, the space behind your eyes. Let the next exhale be the longest one yet. Human spaceflight has never gone farther than the moon. In more than 60 years of crewed missions, no astronaut has traveled beyond that pale, familiar companion in our sky. Every human footprint beyond Earth still belongs to that one small world, barely 250,000 miles away. Compared to the vastness beyond it, the moon is little more than our own backyard. The Apollo missions took about 3 days to reach the moon. Riding atop rockets, astronauts crossed that 250,000 miles in roughly 70 hours, watching Earth slowly shrink behind them. It was, and remains, the greatest distance any human being has ever traveled from home. 3 days was enough to reach the moon. It would take far longer to reach almost anywhere else. Mars sits roughly 225 million kilometers from Earth on average. That distance shifts as both planets circle the Sun, sometimes closer, sometimes much farther apart. Even at its nearest, Mars remains hundreds of times farther than the Moon ever was. It is a red point of light in our sky, and also an entire world's journey away. A one-way trip to Mars with current technology takes about 7 months. For those months, a crew would drift through empty space, farther from any other living soul than humans have ever traveled before. No rescue would arrive quickly. No supply ship would follow soon after. 7 months is the price, today, of reaching our nearest planetary neighbor. Astronauts aboard the space station experience measurable bone and muscle loss. Without gravity's steady pull, bones thin and muscles soften, even with hours of daily exercise built into their routines. The body, so finely tuned to Earth's weight, begins to forget it. Researchers still study how much of this loss can ever be fully reversed after return. Long-duration spaceflight causes documented changes to eyesight. Fluid shifts inside the body without gravity to hold it in place, and pressure builds gently behind the eyes. Many astronauts return with altered vision that does not always fully resolve. It is one of the quieter costs of leaving Earth, discovered only once humans began staying in orbit for months at a time. Cosmic radiation exposure increases cancer risk for astronauts. Beyond Earth's protective embrace, charged particles from the Sun and from deep space pass more freely through skin and bone. Over months or years, that exposure adds up in ways still being carefully measured. It is a slow, invisible toll, counted not in moments but in decades to come. Earth's magnetosphere shields humans from most cosmic radiation. This invisible field, generated deep within our planet's molten core, wraps around us like a vast, quiet umbrella. It deflects the harshest particles the Sun and galaxies send our way, particles that would otherwise reach every living thing below. We rarely think of it, yet it has sheltered every breath we have ever taken. Beyond low Earth orbit, radiation shielding becomes a major engineering problem. Once a spacecraft leaves that protective magnetic embrace, it must carry its own defense against a harsher sky. Thick walls add mass, and mass is costly to carry across such distances. Engineers continue searching for lighter, cleverer ways to keep a crew safe once Earth's shelter is left behind. Encircling our planet, 2 great donut-shaped belts of radiation hold trapped particles in place. Physicist James Van Allen discovered them in 1958 using data from one of the first American satellites. Charged particles from the Sun get caught in Earth's magnetic field and swirl there, dense and energetic. Any spacecraft passing through must move quickly and shield carefully to keep its crew safe from that invisible storm. Let your body grow heavy now, the way sand settles at the bottom of still water. Feel your feet first, sinking into the mattress, then your calves, your knees, releasing their small tensions one by one. The heaviness climbs upward through hips and chest until even your shoulders feel too tired to hold their shape. Your head rests fully now, no longer lifted by any thought. Everything in you has permission to be heavy and to stay that way until morning. NASA's Artemis program intends to carry astronauts back to the lunar surface for the first time since the Apollo era. Named for the Greek goddess of the moon, the program plans crewed landings near the lunar South Pole, where ancient ice may hide in permanent shadow. Early Artemis missions have already tested new rockets and capsules without crew aboard. It is, in many ways, a slow and careful rehearsal for humans, venturing farther than the moon ever again. SpaceX built its Starship vehicle to be reused again and again, landing itself back on Earth after every flight. Older rockets were discarded after a single launch, their enormous cost burned away in minutes. Starship's engineers hoped that recovering and refueling a rocket, much like an airplane, could make spaceflight dramatically cheaper. Whether it succeeds at that scale remains to be proven, but the ambition itself marks a quiet shift in how humanity thinks about leaving Earth. Ion thrusters push a spacecraft forward with barely more force than the weight of a sheet of paper resting on your hand. Instead of burning fuel violently, they use electric fields to accelerate charged particles out the back, a whisper of thrust sustained for months or years. Over time, that patient push adds up to remarkable speeds. It is propulsion built not for haste, but for endurance, trading power for efficiency across the long quiet of deep space. NASA's Dawn spacecraft carried ion engines that let it do something no previous mission had managed. It orbited not one but two distant worlds, the asteroid Vesta and the dwarf planet Ceres, using its thrusters to slow down, adjust course, and settle into orbit around each in turn. Dawn's journey unfolded over nearly a decade, unhurried and precise. Its quiet engines proved that patience itself could be a form of propulsion. In the 1960s, engineers at a program called NERVA built and fired nuclear thermal rocket engines on the ground in the Nevada desert. Instead of burning chemical fuel, these engines heated hydrogen propellant using a nuclear reactor, producing far more thrust for each pound of fuel carried. The tests proved the concept could work, roaring to life in the open desert air. Yet no nuclear thermal rocket has ever carried a human being into space. A nuclear thermal rocket could shorten the journey to Mars by weeks, perhaps months, compared to today's chemical engines. Faster transit means less time exposed to cosmic radiation and reduced strain on a crew's body and mind. Engineers still study how to make such reactors light and safe enough for a real mission. The physics has long been settled. The engineering, careful and incremental, continues even now. A solar sail needs no fuel at all, only sunlight. Photons carry a tiny momentum, and when they strike a vast, thin mirror stretched hot in space, they push it forward, ever so slightly, with each passing moment. The push is faint, gentler than a breath, but in the frictionless dark of space it never stops. Over months, that endless faint pressure can carry a spacecraft to considerable speed. The Planetary Society's LightSail spacecraft, no larger than a loaf of bread, unfurled a reflective sail in low Earth orbit and proved the idea could truly work. Launched in the 2010s, it raised its own orbit measurably using nothing but sunlight pressing against its silver surface. Small cameras aboard captured images of the sail catching the light, unmistakably real. It was a modest experiment with an outsized message about what patient physics can accomplish. Parker's solar probe holds the record as the fastest object humanity has ever built. Launched to study the sun's outer atmosphere, it dives closer to our star than any spacecraft before it. Each close pass uses the sun's own gravity to fling it forward, adding tremendous speed with every loop. Engineers designed a heat shield thick enough to withstand temperatures that would vaporize most machines. Nothing else made by human hands has ever moved so fast. At its closest approach, Parker Solar Probe reaches speeds near 690,000 kilometers per hour. That is fast enough to travel from New York to Tokyo in under a minute. The sun's gravity does most of the work, pulling the probe into a tightening curve with each orbit. Even at such astonishing velocity, the distances beyond our solar system remain almost impossibly vast. Speed, it turns out, is relative to the scale of the universe around it. Somewhere in the house, a low hum settles into the walls, rising and fading like a tide, that never quite reaches shore. It might be the wind finding a gap in the window frame. It might be nothing at all, just the building easing its bones as the night deepens. There is no need to trace its source. Let it arrive, let it recede, let it become the sound of everything slowing down around you. Even traveling at Parker Solar Probe's remarkable speed, a journey to Alpha Centauri would still take more than 6,000 years. The nearest star system lies so far away that our fastest achievements barely register as progress across such a gap. A civilization could rise and fall many times over before such a ship arrived. The scale of interstellar space humbles even our proudest engineering. Distance, out there, answers to nothing but time. Kilometers lose their usefulness once we leave the neighborhood of the sun. Astronomers instead measure interstellar distances in light years, a unit built from the speed of light itself rather than any ruler on Earth. It describes not just distance but time, since the light we see left its source long before it reached us. Thinking in light years reshapes how the mind holds space. It turns the sky into a kind of layered history, told all at once. A single light year stretches across roughly 9.46 trillion kilometers. Written out, the number becomes almost meaningless, a string of digits too large for intuition to grasp. It helps instead to think of it as the distance light itself covers in a full year of unbroken travel. Even moving at that staggering rate, light takes years, sometimes millennia, to cross the space between stars. The universe measures itself in units built from its own fastest possible motion. Far beyond the planets, past even the icy wanderers of the outer solar system, lies a theoretical boundary called the Oort cloud. It marks the edge where the sun's gravity finally loosens its grip on drifting bodies of ice and rock. No spacecraft has ever imaged it directly, since it lies scattered so thin and so distant. Astronomers infer its presence mostly from the long looping paths of certain comets. It is less a wall than a slow fading of influence. Voyager 1, humanity's farthest traveler, has still not reached that distant boundary. It has already passed beyond the influence of the sun's charged particles, entering the space between stars. Yet the Oort cloud extends so far outward that Voyager remains, in a sense, only at the beginning of a much longer crossing. The spacecraft continues onward regardless, sending back faint signals from a silence few instruments have ever touched. At its current speed, Voyager 1 would need roughly 300 more years just to reach the inner edge of the Oort cloud. Its instruments will likely fall silent long before that milestone arrives, its power source fading into eventual quiet. It will continue drifting nonetheless, carrying its golden record of Earth sounds into the dark. 300 years is a modest span for the universe, though a long stretch of decades for those of us who launched it. Among the thousands of worlds discovered beyond our solar system, Proxima Centauri b holds a special place as the nearest known exoplanet. It circles Proxima Centauri, the small red star that makes up part of the Alpha Centauri system, our closest stellar neighbor. Its orbit brings it far closer to its star than Earth sits to the Sun, since red dwarfs burn cooler and dimmer. Even so, the planet's very existence reshaped how astronomers imagine the space just beyond our own doorstep. This small rocky world sits inside what astronomers call the habitable zone of its star, the narrow band where liquid water could theoretically persist. Because Proxima Centauri burns so dim, that zone huddles close, far tighter than the orbit Earth traces around the Sun. Whether Proxima b actually holds oceans or any atmosphere at all remains unknown. Its closeness to us, astronomically speaking, keeps it a favorite subject of quiet speculation among those who study distant worlds. Breakthrough Starshot is a proposed project imagining a fleet of tiny probes launched toward Alpha Centauri. Each probe would weigh little more than a few grams, a sliver of circuitry no larger than a postage stamp. The idea traces back to a group of scientists and engineers who began outlining it in the 2010s. Nothing has yet been built or launched. It remains, for now, a careful architecture of possibility rather than hardware. To move those featherlight probes, Starshot envisions vast arrays of lasers fixed to the ground, firing in unison toward a sail thinner than a soap bubble. The combined beam would push the sail forward, the way wind fills a cloth, except with light instead of air. Once launched, the probe would coast onward without further propulsion, carried by momentum alone. The lasers would only need to fire for a few minutes before their work was done. Let warmth begin at your feet now, spreading upward like something poured slowly through a glass. Feel it settle into your ankles, then rise into your calves, unhurried, taking its time. Let it climb through your knees, into your thighs, filling each inch it touches. Let the warmth reach your hips, your low back, your stomach, rising further still. Wherever it moves, let that part of you grow heavy, sinking into the bed beneath it. The design goal for Starshot's probes is to reach about 20% of the speed of light. That is a staggering fraction, faster than anything humans have ever built. At such speed, a probe would cross more distance in a single second than a jetliner covers in a full day. Reaching that velocity would still leave it far short of light speed itself, yet closer to it than any object in history. Traveling at that speed, a probe could reach Alpha Centauri in roughly 20 years. Compare that to the tens of thousands of years a probe using today's rocket technology would require. 20 years is a span a person could watch unfold within their own lifetime, a child growing into adulthood while the signal crosses the dark. It would still take another 4 years for any message to travel back, carried home at the ordinary speed of light. Building a laser array powerful enough to achieve this remains an unsolved engineering problem. The beams would need enormous, precisely coordinated power, far beyond what any facility on Earth currently produces. Atmospheric turbulence, cost, and the sheer scale of the infrastructure all stand as open obstacles. Engineers continue to study the concept, but no working prototype yet exists at anything close to the necessary scale. Long before Starshot in the 1970s, a group of British engineers undertook a study known as Project Daedalus. Their task was to design, on paper, an unmanned probe capable of reaching a nearby star within a human lifetime. The team worked for several years, publishing detailed technical reports rather than building any hardware. It stands as one of the earliest serious attempts to treat interstellar travel as an engineering question rather than a dream. Daedalus proposed something called nuclear pulse propulsion, powered by tiny pellets of fusion fuel. Each pellet would be ignited in rapid sequence, thousands of controlled detonations pushing the craft steadily forward. The design called for 2 engine stages. The first, burning away before the second, carried the probe onward at greater speed. No fusion pellet engine of this kind has ever been built or tested. Around the same era, an earlier and more radical idea took shape under the name Project Orion. Its proposal was almost startling in its simplicity: propel a spacecraft forward by detonating small nuclear bombs behind it, one after another. A heavy pusher plate would absorb each blast, translating the shock into steady thrust. On paper, the concept promised remarkable speed. In practice, it raised concerns that would soon bring the idea to a quiet halt. The Orion concept found a devoted advocate in physicist Freeman Dyson, who studied it closely through the 1950s and into the 60s. Dyson had a gift for taking wild ideas seriously, and he ran the numbers with patient rigor. His calculations suggested the physics could work, that a bomb-propelled ship might one day cross vast distances. Yet even as the mathematics held up, Dyson himself grew quietly uneasy about the human cost of building such a thing. Nuclear pulse propulsion never left the drawing board, and treaty restrictions are a large part of why. As detonation-based designs matured on paper, the world around them was moving toward limiting nuclear explosions altogether. Any test of an Orion-style engine would have meant setting off bombs in the atmosphere or in orbit. That single requirement collided directly with the diplomatic mood of the era, and the idea drifted from possibility into archive. In 1963, the Partial Test Ban Treaty placed firm limits on nuclear testing in the atmosphere, in space, and underwater. Nations signed it in the shadow of growing concern about fallout drifting across borders. The treaty did not mention spacecraft at all, yet its reach was wide enough to make any bomb-driven engine essentially unbuildable within its terms. What had been an engineering question quietly became a diplomatic one instead. Fusion propulsion, unlike its bomb-driven cousin, remains a live theoretical possibility, even though nothing of the kind has ever been built. The idea is to harness the same reaction that powers stars, releasing it in a controlled, continuous stream rather than a single blast. Engineers have sketched reactor designs and exhaust configurations for decades. Containing a fusion reaction long enough and channeling its energy efficiently remains an unsolved engineering puzzle on Earth, let alone aboard a moving ship. Somewhere above, a thin trail of dust hangs motionless in a shaft of light, suspended as if time itself had paused to hold it there. It does not fall, it does not hurry, it simply floats, catching the light and releasing it again, unbothered by anything beneath it. Your breath can move like that dust now, drifting without direction, needing nowhere to land. Let it hang there, weightless, while the rest of you sinks into the mattress. Antimatter propulsion holds a strange appeal because of its energy density, unmatched by anything chemical or nuclear. When matter meets its antimatter counterpart, both vanish completely, converting their entire mass into pure energy. A tiny amount could, in theory, outperform engines many times its size. The physics is sound and well understood. The challenge lies entirely in getting enough antimatter to work with in the first place. Producing antimatter today is an extraordinarily slow and costly process, nothing like scooping fuel from a tank. Particle accelerators must smash particles together at tremendous energies, hoping a few antimatter particles emerge from the wreckage. Collecting and storing them safely takes specialized magnetic traps, since any contact with ordinary matter destroys them instantly. The entire process at current technology yields only the faintest trace of usable material. At the European laboratory known as CERN, antimatter is made only in minute quantities, purely for research rather than for power. Physicists there have created and studied antihydrogen atoms, learning about their properties in careful, contained experiments. The amounts produced are almost impossibly small, measured in mere billionths of a gram over long periods. No facility on Earth today produces antimatter anywhere close to a fuel-worthy scale. A single gram of antimatter, meeting an equal gram of ordinary matter, would release an amount of energy that dwarfs conventional fuel by comparison. The reaction converts mass directly into energy, following the same relationship Einstein once described. In theory, such a reaction could power a spacecraft far beyond what any chemical engine could achieve. In practice, humanity has never produced anywhere near that much antimatter, nor found any safe way to store it for long. Fusion-powered rockets, if they could ever be built and sustained, might reach a meaningful fraction of the speed of light. Continuous fusion thrust, applied patiently over months or years, could push a ship to speeds chemical engines cannot approach. Such velocities would still fall short of light speed itself, but they could shorten interstellar journeys from millennia to something closer to a human lifetime. The engineering to achieve this remains entirely theoretical for now. Physicist Robert Bussard proposed in 1960 a starship that would not need to carry its own fuel. His design imagined a vast funnel-shaped field, scooping up hydrogen atoms scattered through the space between stars. That hydrogen, fused inside the ship, could theoretically power a journey without limit, since the fuel would be gathered along the way rather than stored from the start. The idea offered a tantalizing answer to one of spaceflight's oldest constraints. Engineers who studied the ramjet closely found problems that resisted easy solutions. The very field meant to gather fuel would also create drag, slowing the ship as it tried to accelerate. Collecting hydrogen efficiently at high speed proved far harder than early sketches suggested, since the atoms arrive scattered and faint rather than in any convenient stream. Decades of analysis have never fully resolved whether such a scoop could work at all. Space between the stars is emptier than most imagination allows. A single cubic centimeter out there might hold only one hydrogen atom, sometimes less. To gather enough fuel for meaningful thrust, a ramjet would need a collecting area so enormous it strains belief, stretching across hundreds of kilometers. The thinness of that medium remains the quiet obstacle beneath every version of the ramjet dream. Time itself behaves differently for anyone moving close to the speed of light. A traveler aboard a very fast ship would age more slowly, according to their own clock, than someone remaining on Earth. This is not illusion but a measured feature of the universe, arising from how space and time intertwine. The faster the journey, the wider the gap between two clocks becomes. High above Earth, GPA's satellites carry this effect written into their daily operation. Their onboard clocks run faster than clocks on the ground, both from their speed and from weaker gravity at orbital altitude. Engineers correct for this constantly, adjusting the satellite's timing so that navigation stays accurate to the meter. Without that correction, positioning errors would grow by kilometers within a single day. Let your jaw loosen now, the way a hand opens when it finally sets something down. Feel the small muscles around your eyes stop holding their shape. Your eyelids grow heavy, not because you are tired, but because they have simply run out of reasons to stay lifted. Behind them, the dark widens, private and unhurried, asking nothing of you at all. Stay there a while, in that warm, unlit room behind your own closed eyes. Aboard a ship traveling near light speed, a crew might live through only a handful of years, while Earth moved through decades. Grandchildren could grow old before the travelers themselves showed any sign of aging. This is not a trick of imagination, but a real consequence of relativity, one that would separate a crew from everyone they once knew, even as their own lives felt ordinary and continuous. The stars would carry them forward while time on Earth ran far ahead. Nothing built by human hands has ever come close to these speeds. Even the Parker Solar Probe, the fastest object humanity has launched, travels at only a small fraction of light speed. The gap between our fastest machines and relativistic velocity remains vast, spanning many orders of magnitude. Every spacecraft launched so far has stayed well within speeds that time dilation barely touches. Reaching even a modest fraction of light speed would demand energy on a scale beyond anything humanity currently produces. The faster a ship needs to go, the more propellant and power it must carry, and that added mass itself requires more energy to move. This spiral of demand grows quickly, turning a simple speed goal into an almost impossible engineering equation. No fuel source known today could supply what such a journey would require. The energy needed to accelerate a spacecraft does not rise gently as speed increases, it rises sharply. Reaching half the speed of light demands far more than twice the energy of reaching a quarter of it, and pushing closer to light speed multiplies that demand again. This steep curve is written into the physics of relativity itself, growing without any known ceiling. It is this curve, more than any single missing technology, that keeps interstellar travel just beyond reach. Generation ships describe a proposed way to cross the vast gap between stars. A single crew departs, but no one aboard ever completes the voyage. Children are born, grow old, and pass the mission forward like a torch. The ship itself becomes a small, self-contained world carrying its own history and its own future. No such vessel has ever been built, but the idea has shaped decades of serious engineering thought. A generation ship bound for Alpha Centauri could take well over 100 years to arrive, even at speeds far beyond anything built today. Depending on the propulsion imagined, the journey might stretch across 4, 6, or even more human generations. Those who arrive would be the descendants of those who left, never having known Earth themselves. The destination would be inherited, not chosen. Closed ecological life support systems, which recycle air, water, and food without outside resupply, have only ever been tested at small scale. A handful of experiments have sustained a few people for months at most. No system has proven it can sustain a crew and their children for generations without failure. The gap between a laboratory trial and an interstellar lifetime remains largely untested. In the Arizona desert during the 1990s, a project called Biosphere 2 enclosed several people inside a sealed glass structure for 2 years. Inside, they grew their own food, recycled their own water, and breathed air produced by their own plants. It stood as one of the most ambitious attempts ever made to test a self-contained living system. The experiment revealed both what was possible and what was still poorly understood. Inside that sealed structure, oxygen levels fell far faster than anyone had predicted, eventually dropping low enough to affect the health of those living there. Investigators later traced much of the loss to concrete inside the dome, which had quietly absorbed oxygen through a chemical reaction no one had accounted for. The mystery took months to solve. It showed how easily a closed system can behave in ways its designers never anticipated. Keeping a population genetically healthy across many generations aboard a single ship poses a real and stubborn problem. A crew too small risks inbreeding and the slow loss of genetic variation. Population geneticists have studied minimum numbers for exactly this reason, often suggesting crews in the thousands rather than the dozens once imagined in early proposals. Even then, isolation itself, sealed away from any other human population, remains a challenge with no fully settled solution. Let your breath find its own rhythm now, without any effort to guide it. Notice the small pause at the top of the inhale and the longer, looser release that follows. Each exhale can grow a little longer than the one before, unhurried, like a tide easing back from shore. There is no need to count, no need to shape it. Just let the next breath come when it wants to, and the one after that, further and further from waking. Shielding a generation ship from cosmic radiation would require enormous mass, likely more than the living quarters themselves. Thick layers of water, dense metal, or packed regolith have all been proposed as barriers, each adding weight that must then be accelerated across the stars. The heavier the shield, the more energy the whole journey demands. This trade-off between protection and propulsion remains one of the largest unsolved puzzles in every generation ship design. Suspended animation, the idea of slowing human biology for a long voyage, has never been demonstrated to work. Popular imagination has long pictured travelers sleeping through the decades, waking only near arrival. Real biology offers no proven way to safely lower human metabolism for years at a time. Every serious study on the subject ends with the same honest conclusion: the technology simply does not exist yet. Tardigrades, tiny eight-legged creatures barely visible to the naked eye, can survive extreme dormancy far beyond what any human body could endure. They can dry out almost completely, halt their metabolism, and remain that way for years, only to revive when moisture returns. Some have even survived direct exposure to the vacuum of space, Their resilience offers biologists a rare glimpse into what extreme dormancy might one day look like if it were ever possible for something as complex as a human. NASA has funded research into torpor, a state of lowered metabolism borrowed from hibernating animals, as a possible way to keep deep space crews stable during long voyages. Engineers see practical appeal in torpor: less food, less water, smaller living space, fewer psychological strains from months of isolation. Small mammal studies have shown real promise. Applying the same biology safely to humans, though, remains an early and unfinished chapter of aerospace medicine. Cryonics, the freezing of a human body in hope of future revival, has never once succeeded in bringing anyone back. Companies preserve bodies in liquid nitrogen, believing future medicine might reverse the damage of freezing and death itself. No laboratory anywhere has restored a frozen mammal as complex as a human to life. The promise remains frozen too, suspended between hope and unproven science. Spinning a spacecraft to create artificial gravity has been proposed since the early days of rocketry, yet no such structure has ever been built at meaningful scale. The physics is simple enough. Rotation pushes bodies outward, mimicking the pull we feel on Earth. Building something large enough to spin safely, without shaking itself apart, has stayed on paper. Engineers still weigh cost against comfort, decade after decade. Fast rotation, strong enough to mimic full Earth gravity, would likely leave a crew dizzy and disoriented. The culprit is something called the Coriolis effect, a subtle twisting force that grows stronger as spin rate increases. Turn your head too quickly aboard a tightly spinning station, and the whole world seems to tilt sideways. Designers must slow the spin and widen the ring simply to keep human balance intact. The great rotating wheel station, imagined in classic science fiction, slowly turning against the stars, has never left the realm of concept art. Its calm, graceful spin still shapes how many people picture the future of space travel. Real budgets, real materials, and real orbital mechanics have kept it purely theoretical. It remains, for now, one of the most beloved designs never built. Astronauts aboard the International Space Station have successfully grown lettuce, radishes, and a handful of other small crops in specialized growth chambers. Each plant floats in a carefully engineered tray, roots wrapped around fibrous pads instead of soil. The yields stay modest, and the variety stays narrow. Still, every harvest offers a small proof that life can take root, even in orbit. Beyond leafy greens, researchers explore insects and lab-grown cells as denser, more efficient sources of nutrition for future deep space missions. Crickets and mealworms convert feed into protein far more efficiently than cattle ever could. Cultured muscle cells, grown in bioreactors, offer another path entirely, sidestepping the need for pastures or soil altogether. Neither idea has fully left the laboratory, but both hint at how future travelers might eat among the stars. Feel the weight of your body now, settling deeper into whatever is holding it. Your shoulders release first, sinking a little further with each breath. Then your arms grow heavy, resting fully, asking nothing more of you. Your legs follow, loose and unmoving, sinking into softness beneath them. Even your hands seem to grow heavier, forgetting the need to hold anything at all. Let this heaviness spread all the way down, all the way through, until your whole body feels like it belongs to the surface beneath it. Water aboard the International Space Station rarely goes to waste. Specialized systems capture moisture from astronaut sweat, breath, and even urine, filtering it through multiple stages until it becomes drinkable again. Nearly every drop gets a second life, cycling endlessly through pipes and filters rather than being resupplied from Earth. It is an unglamorous kind of miracle, one that keeps a crew alive without needing constant deliveries from home. No mission has yet proven that a colony beyond Earth could grow all of its own food, air, and water without support from home. Small experiments have hinted at what is possible, but scaling those systems to feed a self-sustaining population remains untested. Every closed loop tried so far has needed backup, correction, or resupply. Whether life can fully sustain itself away from Earth stays an open and unanswered question. Terraforming Mars remains a concept, not a plan with any proven method. Engineers speak of warming the planet, thickening its air, coaxing rivers back across dry basins. Yet no one has ever done this to a world, not even in miniature. The idea lives mostly in models and hopeful sketches. Mars stays as it has been for ages, red and still under a thin sky. Mars has no global magnetic field strong enough to shield a thickened atmosphere from solar wind. Long ago, its core cooled and its protective field faded away. Without that shield, any new atmosphere built there would slowly be stripped by streams of charged particles from the sun. Earth's own magnetic field does this work quietly, deflecting what Mars can no longer resist. It is one more reason a breathable Mars remains distant and uncertain. To thicken the Martian atmosphere, engineers propose releasing the frozen carbon dioxide locked in its polar caps. Warming those ice deposits could, in theory, release enough gas to raise atmospheric pressure. Sunlight, mirrors, or engineered greenhouse gases have all been suggested as tools for the task. Recent studies suggest the available frozen carbon dioxide may not be enough to finish the job. The polar caps remain untouched, glinting white under a cold, thin sky. No technology currently exists that could terraform a planet within a single human lifetime. Every serious proposal stretches across centuries, sometimes millennia, far beyond any individual's years. Engineers describe timelines longer than recorded history itself. What looks urgent on a screen unfolds, in truth, at a geological pace. Any Mars fit for open air would likely be inherited by descendants of those who first dreamed it. Interstellar travel depends on solving problems that material science has not yet resolved. A ship crossing between stars would face stresses no vessel has ever endured: radiation, extreme cold, and decades of continuous strain. Engineers speak of hulls and shields that do not yet exist outside of drawings. The gap between concept and material reality remains wide. Every serious design waits on breakthroughs still unmade. No material yet exists that could survive repeated collisions with interstellar dust at extreme speed. Even a speck of matter, at a meaningful fraction of light speed, strikes with the force of a small explosion. Engineers have tested composites, layered ceramics, and exotic alloys, and none have proven durable enough. The vacuum between stars is not empty so much as sparsely dangerous. Any ship crossing it would need armor beyond anything built so far. Some designs propose sacrificial shielding, layers meant to burn away as they absorb the impact of interstellar dust. This ablative approach lets the outer surface erode gradually, protecting what lies beneath. Each collision would strip away a little more material, thinning the shield over the length of a voyage. Engineers imagine renewable layers replaced or regrown along the journey. It is a defense built on gradual sacrifice rather than permanence. Magnetic shielding has also been proposed as a way to deflect interstellar debris before it ever touches the hull. A field generated around the ship could, in theory, push aside charged particles and ionized dust. The concept borrows loosely from Earth's own magnetosphere, though scaled and shaped for a moving vessel. No such system has been built or tested at the scales interstellar travel would require. For now, the idea remains a diagram, elegant and unproven. Somewhere beyond the walls, a low hum settles into the air, rising just enough to be noticed, then fading again. It might be wind against the house, or a distant machine breathing through the night. It comes and goes without pattern, without hurry, asking nothing of you. Let your attention rest on it loosely, the way you'd watch a curtain move in a draft. Each time it fades, let your body sink a little further into stillness, following it down toward rest. In 1994, a physicist named Miguel Alcubierre proposed a theoretical solution to Einstein's equations that would allow faster-than-light travel without breaking relativity. His idea imagined a bubble of space contracting in front of a ship and expanding behind it, carrying the ship along like a wave. Inside the bubble, nothing would exceed light speed at all. On paper, the mathematics held together in a startling way, outside of equations. No such bubble has ever been built or observed. The Alcubierre drive would require what physicists call negative energy density, a form of energy with properties unlike anything ever measured. Ordinary matter always carries positive energy, pulling and pushing in familiar ways. Negative energy density would behave differently, warping space itself rather than moving through it. No laboratory has ever confirmed that such energy can exist in usable form. The drive remains bound to a substance that may not be part of our universe at all. Modified warp drive models have been proposed that would need far less exotic energy than Alcubierre's original design. Researchers reworking the mathematics found ways to reshape the bubble, softening its extreme demands. These versions trade some speed or efficiency for a gentler energy requirement. The physics grows more forgiving, though still theoretical. Even the friendliest version of a warp bubble has yet to leave the pages of a journal. Wormholes are theoretical passages through space-time, first suggested by the equations of general relativity itself. They would connect two distant points, folding the space between them like a sheet bent until its ends touch. Einstein and Nathan Rosen described an early mathematical version in the 1930s. In principle, a traveler could step through one side and emerge somewhere impossibly far away. The mathematics permits it, even as nature has given no sign of building one. No wormhole has ever been observed, photographed, or detected by any instrument humanity has built. Telescopes have searched the sky for the gravitational signatures such a structure might leave behind. Nothing resembling one has appeared, not near a black hole, not anywhere in the mapped universe. The concept survives purely within equations, elegant but empty of evidence. It remains a shape drawn on paper, waiting for the universe to agree. A traversable wormhole, one a traveler could actually pass through, would need exotic matter to keep its throat from collapsing. Ordinary matter would pull the passage shut the instant something tried to enter. Exotic matter, with its unusual negative pressure, might hold the opening steady. Whether such matter can exist in sufficient quantity remains unresolved. The wormhole's survival depends on a substance still confined to theory. Quantum entanglement links two particles, so that measuring one instantly affects the state of the other, no matter the distance between them. It sounds like a shortcut around the speed of light, but it isn't one. No usable information travels faster than light through this connection. Physicists have confirmed this again and again, across labs and even across satellites. The entanglement is real, but the shortcut many imagine simply isn't there. Physicists have explored whether a traversable wormhole could, in theory, allow travel backward through time. If one end of the passage moved near light speed while the other stayed still, time dilation might stretch the difference between them. A traveler entering one side could, mathematically, emerge before they left. The scenario raises paradoxes that unsettle even seasoned theorists. No experiment has ever tested it, and none likely could. Whether faster than light travel would violate causality is a question physics has not settled, If something outpaced light, certain reference frames might see effects occurring before their causes. Some theorists treat this as proof that such travel must be impossible. Others wonder whether nature simply forbids the conditions that would ever let it happen. The debate stays confined to chalkboards, calm and unresolved. Tachyons are hypothetical particles imagined to move faster than light by default, born already past the limit rather than accelerated into it. Theoretical physics allows their mathematics to exist without contradiction, at least on paper. No detector, collider, or telescope has ever found a trace of one. They remain a curiosity living entirely inside equations. If they exist at all, the universe has kept them perfectly hidden. Let warmth begin at your feet, spreading upward the way sunlight moves across a floor as morning deepens. Feel it settle into your ankles, then your calves, loosening what the day had tightened. It rises through your knees, unhurried, reaching your thighs like a slow tide filling a low shore. Let it climb into your chest, your shoulders, your hands resting open. Wherever the warmth reaches, let that part of you grow heavy, and let heaviness become rest. A puzzle called the Fermi paradox asks a patient question. Given the vast number of stars and the age of the galaxy, why does the sky stay silent? No radio signal, no visible structure, no confirmed sign of another civilization has ever reached us. Physicist Enrico Fermi is said to have raised the puzzle over lunch in 1950. It remains open, not because the universe is empty, but because we still do not know. Astronomer Frank Drake devised an equation to estimate how many civilizations might be broadcasting across the galaxy right now. It multiplies factors like star formation rates, the fraction of stars with planets, and the odds life becomes intelligent enough to communicate. Each variable remains loosely known, some barely more than a guess. The equation does not give an answer so much as a shape for the question. It has guided the search for 6 decades. Since the 1960s, an effort called the Search for Extraterrestrial Intelligence has listened to the sky for artificial radio signals. Enormous dish antennas have scanned countless frequencies, hoping to catch a pattern too structured to be natural. Decades of listening have produced interesting anomalies, but no confirmed detection. The silence itself has become a kind of data. Researchers continue the search, undeterred by the quiet. A framework called the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, ranks civilizations by how much energy they can harness. A Type 1 civilization uses the energy available on its home planet. A Type 2 reaches further, drawing from its entire star. A Type 3 would command the energy of a whole galaxy. Humanity, by most estimates, has not yet reached even the first rung. A civilization at the second tier of the Kardashev scale would draw upon the entire energy output of its star, not merely the sunlight that happens to fall on a planet. That is a staggering quantity, more power in an instant than humanity has used across its whole history. No evidence suggests any civilization has reached this stage. The idea exists purely as a marker, a distant rung on a ladder we cannot yet see the top of. Physicist Freeman Dyson proposed a hypothetical structure in 1960 that could enclose a star and capture nearly all its radiated energy. Such a Dyson sphere would need to be built from a scale of material far beyond anything mined on Earth. Dyson himself framed it as a thought experiment about energy needs, not a blueprint. The idea nonetheless captured imaginations for generations. It remains a symbol of what advanced engineering might someday attempt. Telescopes have searched stellar light for the faint infrared signature a Dyson sphere might leave behind, waste heat escaping from an enclosed star. No such signature has ever been confirmed. Some unusual dimming patterns have briefly raised curiosity. later explained by dust or natural stellar behavior. The absence of evidence has not ended the search. It has simply kept the question gently open, unresolved among the stars. Rather than a single unbroken shell, some designs imagine a Dyson swarm, a great many smaller collectors orbiting a star independently. This version avoids the structural nightmare of building one continuous sphere. Each piece could be built, launched, and positioned separately, growing the system gradually over time. Engineers favor this approach in thought experiments, since it demands far less material all at once. It remains, like its counterpart, entirely theoretical. Mathematician John von Neumann described machines in the 1940s, capable of building copies of themselves from raw material. Applied to space exploration, this idea became the von Neumann probe, a hypothetical spacecraft that could land, gather resources, and construct another version of itself before moving on. Each new probe would repeat the process elsewhere. No such device has ever been built. It lives only in engineering papers and quiet speculation. If a single self-replicating probe could reach even a modest fraction of light speed, its descendants could, in principle, spread across the galaxy far faster than any single ship ever could. Each new probe doubling the frontier, then doubling again, growing outward like a slow root system through the dark. Models suggest such an expansion could cover the galaxy within a few million years, a span vast to us, brief on a cosmic clock. The concept remains a calculation, never yet a reality. Let the breath fall lower now, past the chest, into the quiet weight of the belly. Somewhere, a candle has just been pinched out, and its last thread of smoke curls upward, softening, thinning, disappearing into the dark air of the room. There is nothing to follow in that smoke, no shape to hold. Let your thoughts do the same, rising once, then fading, then gone. No self-replicating spacecraft has ever been built. The von Neumann probe remains, for now only a careful sketch in engineering journals. Building a machine that can mine, refine, manufacture, and assemble another version of itself demands technologies still scattered across separate laboratories, never joined into one working whole. The idea persists because it is elegant, not because it has been proven possible. It waits patient on paper. Panspermia theory suggests life could spread between star systems naturally, carried on drifting rock and ice. A microbe embedded deep within a meteorite might survive the cold vacuum of space, shielded from radiation by layers of stone. Over millions of years, such fragments could travel between worlds, seeding life where conditions allow. No confirmed case has ever been found. The idea remains a quiet possibility, drifting at the edges of biology. Directed panspermia proposes something bolder, that life could be sent between stars on purpose rather than by chance. Biologist Francis Crick once suggested a civilization might deliberately launch hardy microorganisms toward distant planets, hoping they would take root. It remains untested and unproven, a thought experiment rather than a mission. Still, it reframes an old question gently, asking whether life's spread might one day be a choice rather than an accident. Interstellar objects like Oumuamua have been observed passing through our solar system. Brief visitors from beyond. Detected in 2017, it arrived on a path that could only have originated outside our star's gravity, tumbling through on a trajectory bent by nothing local. Telescopes tracked it for only a few weeks before it slipped back into the dark. It was the first such object ever confirmed, a fleeting guest from somewhere unknown. Oumuamua's unusual shape sparked speculation, though most scientists attribute it to natural origin. Its elongated form and slight unexplained acceleration led a few researchers, including astronomer Avi Loeb, to wonder aloud whether it might be artificial. The broader field points instead to outgassing ice or unusual rotation as likely, ordinary explanations. The debate never fully closed, but the evidence leans quietly toward nature rather than design. Multi-generational interstellar migration has been modeled mathematically but never attempted. Researchers have calculated population sizes, radiation exposure, and genetic diversity needed to keep a crew viable across centuries of travel. The numbers suggest it could work, in principle, with careful planning and enough redundancy. No ship has ever tested these models against reality. They remain equations on a page, patient and unhurried, waiting for engineering to catch up with imagination. Some proposals suggest sending frozen embryos rather than living adults to new star systems. A small craft carrying thousands of embryos in cryogenic storage would need far less mass, food, and life support than a crew of grown humans. Robotic systems would handle the long wait, then oversee birth and early care upon arrival. It remains speculative, resting on technologies not yet perfected, but it quietly reframes what a voyage might even require. Artificial wombs remain experimental and unproven for full human gestation. Laboratory work has kept premature lambs developing inside fluid-filled chambers for weeks, a hopeful but partial step. Extending such technology to carry a human pregnancy from its earliest days to birth has not been achieved. The gap between promising animal studies and full human application stays wide. It is a field still learning, one careful experiment at a time. Some researchers propose sending digital human minds instead of physical bodies. Rather than transporting flesh across the centuries, a ship might carry only data, patterns representing memory, personality, and thought to be reconstructed on arrival. No such transfer has ever been demonstrated, and whether a copied mind would feel like a continuation of a self remains unanswered. It stays a philosophical question wearing the clothing of engineering. Whole brain emulation remains a theoretical concept with no working demonstration. The idea imagines scanning every neuron and synapse of a living brain, then recreating that structure inside a computer. Neuroscience can map small circuits today, cell by careful cell, but a full human connectome has never been captured. Whether a simulated brain would think, feel, or simply calculate replies stays unresolved. For now, the concept lives only in papers and diagrams, decades ahead of the hardware it would need. Let your jaw loosen now, just slightly, the way it does in the deepest part of sleep. Behind your closed eyes, there is only darkness, warm and unmapped, asking nothing of you. Let your eyebrows fall away from each other. Let your lips part, just barely, and let your breath find its own way in and out. The muscles around your eyes have been holding a shape all day. Let them forget it now. Whatever tomorrow needs from you, it can wait outside this room. Some theorists debate whether an uploaded mind would constitute genuine continuity of consciousness. A digital copy could carry every memory, every mannerism, every fragment of a personality, and still raise an old question in new form. Would that awakened pattern be the same person, or only a convincing echo of one? Philosophy offers no settled answer, only competing views on what selfhood truly requires. The original person, meanwhile, could go on living, aware that another version of them now exists somewhere else entirely. Interstellar seed missions have been proposed as a way to jumpstart distant colonies without living crews aboard. In this vision, small robotic ships would carry genetic material, construction equipment, and artificial intelligence rather than people. Landing on a chosen world, machines would begin preparing an environment long before any human arrived. Whether such missions could function unsupervised across centuries stays untested. The idea reframes colonization as something machines could begin first, with people arriving generations later to what was already prepared. Detecting biosignatures on distant exoplanets remains technologically challenging with current telescopes. Astronomers look for subtle chemical fingerprints in starlight passing through a planet's atmosphere, traces of oxygen, methane, or other gases that could hint at life. The signals are faint, buried in light that has traveled trillions of kilometers to reach a mirror on Earth or in orbit. Current instruments can detect some atmospheric gases, but rarely with the certainty needed to declare life confirmed. Better telescopes, still being built, may narrow that gap in the years ahead. Some habitable zone exoplanets have been detected using the transit method. As a planet crosses in front of its star, it dims that star's light by a small, measurable amount. Watching for that faint dimming, repeated on a steady rhythm, tells astronomers a planet is there and roughly how large it is. From such dimming patterns, scientists have found planets orbiting at distances where liquid water could exist. It is a method built on care and repetition, watching the same star for years without looking away. TRAPPIST. One hosts several roughly Earth-sized planets in a compact system. The star itself is a small, cool red dwarf, far dimmer than the Sun. Around it circle 7 known worlds, packed so closely that from one planet's surface, neighbors could appear larger than the Moon does from Earth. 3 or more of these worlds sit within a zone where temperatures could allow liquid water. The whole system fits inside a space smaller than the orbit of Mercury around our Sun. The Kepler Space Telescope discovered thousands of exoplanet candidates. Launched in 2009, Kepler stared at a single patch of sky for years, watching more than 100,000 stars at once. It measured tiny dips in starlight, the telltale signature of planets passing across their stars' faces. By the time its mission ended, Kepler had confirmed over 2,000 worlds and flagged thousands more awaiting confirmation. It transformed exoplanets from rare discoveries into an ordinary feature of the galaxy's night sky. Most known exoplanets orbit stars many light-years beyond Alpha Centauri. The closest confirmed worlds circle our nearest stellar neighbors, but the bulk of the known catalog lies scattered across a small patch of the Milky Way, hundreds or thousands of light-years distant. Even the nearest of these systems would take existing spacecraft tens of thousands of years to reach. The galaxy, it turns out, is thick with planets, though thin with any hope of visiting most of them soon. Red dwarf stars, the most common type, often produce dangerous flares for nearby planets. More than 70% of stars in the Milky Way are faint red dwarfs, small and long-lived compared to the Sun. Their habitable zones sit close in, tucked near the star for warmth, but that closeness brings danger. Red dwarfs often erupt with flares far stronger relative to their size than anything the Sun produces, blasting nearby planets with radiation and charged particles. A world circling one of these stars would need a strong magnetic field just to keep its atmosphere intact. Stars like our Sun make up only a small fraction of the galaxy's population. Most stars are smaller, cooler, dimmer red dwarfs, while Sun-like stars burn brighter and steadier, offering wide habitable zones with fewer violent flares. Yet they are rarer, scattered thinly among the galaxy's more common small stars. A civilization searching for a truly stable, Earth-like haven finds fewer candidates than the sky's sheer number of stars might suggest. Certain calculations suggest a handful of nearby star systems might be reached within a few centuries if propulsion technology advanced far beyond anything built today. These models imagine engines using fusion, antimatter, or beamed energy, pushing spacecraft to a meaningful fraction of light speed. Under such assumptions, Alpha Centauri, Barnard's star, or other close neighbors could fall within reach of a single long human lifetime, or a few generations at most. The numbers remain theoretical, built from hope and physics rather than hardware. Let your exhale grow a little longer than your inhale, again and again, until the counting itself fades away. Each breath out can carry a small weight from your shoulders, your jaw, the space between your eyebrows. There is no need to breathe a certain way, only to notice the air moving, unhurried, filling and emptying like tide against a shore that never keeps score. Let the next breath come on its own. Let the one after that come slower still. Before humanity could carry itself between stars, it would likely need industry that no longer depends on Earth at all. Mining, manufacturing, and energy production would need footholds beyond the home planet, supplying materials and fuel without a single launch from the ground. Building a starship, in this view, begins not with a rocket, but with factories, orbiting far from any planet's surface. Earth would become one workshop among several, rather than the sole source of everything. Asteroids drifting through the solar system carry metals, water, and other raw materials that could support construction far from Earth. Mining these bodies has been proposed as a way to supply future spacecraft and habitats without hauling every resource up from the ground. Water locked in icy asteroids could become fuel, breathable air, or drinking water for crews working far from home. The asteroid belt in these proposals becomes less an obstacle and more a quarry. No company or nation has yet pulled a single ounce of usable material from an asteroid for practical use. Several missions have visited these bodies, some collecting tiny samples for scientific study, but none have returned resources meant for building or fueling anything. The idea remains a plan on paper and in models, tested only at the smallest experimental scale. The asteroid belt's riches, for now, stay untouched by any true mining operation. Engineers have proposed assembling large spacecraft piece by piece in orbit, rather than launching a finished ship in a single towering rocket. Components could be lifted separately, then joined together by robotic arms or human crews, working weightless, free from the stresses of a rocket launch. This approach could allow ships far larger and more fragile than anything built to survive the violence of liftoff. A vessel meant for the stars might never touch the ground at all. An O'Neill cylinder is a hypothetical design for a giant rotating cylinder in space, spinning to create artificial gravity along its inner walls. Proposed by physicist Gerard O'Neill in the 1970s, the concept imagines a habitat large enough to hold farmland, rivers, and thousands of residents living along its curved interior. Sunlight would enter through long windows, and the slow spin would press inhabitants gently against the walls, mimicking the pull of a planet. It remains one of the most detailed visions of a home built entirely from scratch in space. No structure resembling an O'Neill cylinder, or any habitat of similar scale, has ever been built. The concept remains confined to drawings, calculations, and the occasional detailed engineering study. Building one would require assembling far more material in orbit than humanity has ever moved beyond Earth's surface. For now, the largest home in space remains a modest station, a fraction of the size these old designs once imagined. A few forward-looking thinkers wonder whether spreading across several star systems might happen before any single disaster could end humanity's story on Earth. Extinction-level threats, cosmic or self-made, could in theory be outrun by simply existing in more than one place at once. This idea treats interstellar travel less as adventure and more as insurance, a way of holding more than one candle against the dark. Whether such spreading could happen quickly enough remains entirely unresolved. The long-term survival of any spacefaring species remains a purely speculative question. No civilization anywhere has yet proven it can outlast its own planet. Cosmology offers no promise that intelligence, once it arises, continues indefinitely. Whether survival depends on reaching other worlds or simply enduring at home remains unknown. The universe keeps no record of outcomes, only of possibilities still open, waiting to be lived out or left unfinished. Certain theorists argue interstellar expansion may be the ultimate filter civilizations must pass. Spreading beyond one star in this line of thought could be harder than any technical leap that came before it. Civilizations that cross it may continue across whole eras. Those that cannot may simply end where they began. No evidence confirms the idea, yet it remains one way to explain why the sky appears empty of neighbors. Whether humanity ever becomes an interstellar species remains an open and unresolved question. No law of physics forbids the journey, and no timeline promises it either. The stars will wait, as they have for billions of years, whichever answer time eventually gives. For now, your place among them is simply here, beneath this same sky, breathing, safe on a small blue world. Let the vast, unanswered universe hold itself tonight. Rest well. Good night.